All right, welcome back. And as alluded to in the previous video, the topic for this one to continue on then is to look at the CDF. So let's go ahead and dive right in to definition 3.7 for us here with our e-text. The CDF, capital F of X, of a continuous random variable, capital X, with probability density function, little f of x, is as follows. Capital F of x is equal to, this is the same definition for CDF, right? Notice CDF, we didn't change. Cumulative distribution function does not change between, the name doesn't change between discrete and continuous, because it is still literally the probability that your random variable is less than or equal to some other value. But how you compute that probability is different based on whether or not it's continuous or discrete. And in the continuous sense, right, the probability, then we know we have to integrate. So what are we going to integrate to? We're integrating up to an upper bound of little x, right? This means x is less than or equal to little x. So we integrate all the way up to there from minus infinity, if needed. And so this would be f of x d. Well, let's not abuse notation here. We already have little x. So this will be, we'll say f of t dt. There's our CDF definition, okay? A few things to note about the CDF, capital F of x, specifically as it relates to continuous random variable stuff, okay? Capital F is what we call a monotonically non-decreasing function. Monotonically non-decreasing function. Non-decreasing function. What does this mean? Monotonically non-decreasing function means that as x is increasing, as you increase in your independent variable, the function value or output is either staying the same or getting larger, right? It never fluctuates up and down. It is monotonically non-decreasing. We don't necessarily say it's an increasing function because it's not always increasing. It's possible that it stays constant for a while. And specifically, once the CDF hits a value of 1, it'll stay constant at 1 on to infinity. All right. Two, you can use the CDF directly to compute these probabilities. The probability that x is between a and b can be computed exactly using the CDF. In fact, you sort of do without realizing it, because when you compute this using the original definition of a PDF, you're integrating. And what you do when you integrate is you evaluate the antiderivative of the endpoints. Well, that integral, that antiderivative, is the same thing you would get from doing this integral, but you're just plugging in your endpoints. This is capital F of b minus capital F of a. And maybe you're starting to see the suggestive notation now take shape here. And why we've been using little f and big F is because in the continuous case, the familiar calculus notation is consistent in the sense that capital F, your CDF, is the antiderivative, more or less, of the PDF. Now, there's some other domain restrictions, but we'll get to that. Vice versa, the little f, the PDF, the probability density function, little f of x, can be found by simply differentiating then your CDF. You can take the derivative of your CDF and you can go back to your little f, that's your probability density function, okay? All right, enough with that definition. Let's take a look at an example and maybe we can make some more sense out of this, all right? Earlier, in a previous video, we had, in fact, I could just scroll up and look at it if we want to. We had the continuous PDF, f of x is equal to x squared over 3 on the interval minus 1 to 2. And then it was 0 everywhere else, okay? So let's just take that, and let's go ahead and find capital F of x and use it to evaluate use it to evaluate. What did we do in that example? What did we do in that example? Use it to evaluate. So x squared over 3 was right here. Okay, so here's x squared over 3 from minus 1 to 2. And then we use that to find 0 to 1. The answer was 1/9. So let's do that again and make sure we get the same answer. So let's use that to evaluate probability that 0 is less than x is less than 1. All right, here we go. So according to the definition, capital F of x is equal to the integral from minus infinity to x of f of t dt. So how do we translate that into our specific question? Well, in our specific question, we're going to integrate from, we don't need to integrate from minus infinity because we know that the value will be 0 up until we get to negative 1. So we can just go from minus 1 up to x. And then f of t dt, so instead of x squared over 3, we just have t squared over 3, so that when we do the antiderivative, we can plug in x, and we'll get a function in terms of x at the outputs. All right? So the antiderivative here, with respect to t, we've done this one a few times. That's t cubed over 9. Now we evaluate this from minus 1 to x. Plugging in x, then, we're going to get x cubed over 9. Plugging in negative 1, that's minus a negative 1 cubed over 9. Negative 1 cubed we know to be just negative 1. So we have a common denominator of 9. And then we have x cubed minus the negative 1 is x cubed plus 1. X cubed plus 1, all right? So what is the CDF capital F of x in the continuous case here? The CDF is, let me start with the middle. This only holds, this x cubed plus 1 over 9 only holds for these x values. Only works on these x values, right? Because that's where that integral is valid for. So this is x cubed plus 1 over 9 as we go from minus 1 to 2. We go from minus 1 to 2, okay? Now, what should the value of the CDF be outside of these ranges when x is less than or equal to negative 1? Well, there is no positive probability coming from our PDF at that point, so the cumulative distribution there would be 0. And after this, we're not adding any additional positive probability, and so this should actually end up being equal to 1. It should cap out at 1, just like it does in the discrete case. Just like it does in the discrete case. So there's our CDF. CDF, all right? Use it to evaluate the probability that x is between 0 and 1. So let's go ahead and do that then, right? I would say then the probability that x is between 0 and 1. How do we use this to evaluate it? Well, according to this rule, it should just be capital F of b minus capital F of a. So this is going to be capital F evaluated at 2. Sorry, no, not 2. What is B and A here? B, so here's A, and then here's B. So capital F of 1 minus capital F of 0. All right, so what is capital F of 1? That's 1 cubed plus 1 over 9. And then capital F of 0, well, when you evaluate this at 0, that's going to be 0 cubed plus 1 over 9. So that is 2/9 minus 1/9. That is just equal to 1/9, which is the same answer we got in the previous video. There we go. So that looks good. That's our CDF right there. Okay. Let's take a moment to look at this graphically here real quick, the CDF. We can go ahead and get a graph of this. So let me go ahead and start using some of the material that I have. So I want this probably, I'll make it a little bit bigger. There we go, so it can look like that. So here's my x. Let's make this capital F of x. Okay, so there's 1. Let's say there's a half. All right, so where is this really interesting? This is really interesting from minus 1 to 2, and then outside of that where it's kind of uninteresting. So let's go ahead and say here's 1, here's 2, so then minus 1 and minus 2 there, okay? Looks good. All right, so graphing this shouldn't be too bad. When x is less than or equal to -1, it's just going to be equal to 0. So at -1, it's 0, and it looks like this. And then at 2, it's equal to 1. So right there, roughly. And it's going to go on indefinitely like that. In between this, we have this cubic function here. In between this, we have this the cubic function, right? And so let's go ahead. What does that cubic function look like? You can just generally do like a rough sketch of a cubic between these 2 points, or take a look at the graph of that if you want to. Let's see here. I can give us a pretty good image of what that looks like. And we'll zoom in here. You can see this panel on the right. Here's what that graph looks like. So it's just above the axis there. At about 0, the height is about 0.11. And then as we go to 2 here, when x is 2, look at the height go to 1. And so you've got a nice smooth connection right there at 2, 1. At 2, 1, you got a nice smooth connection there. All right, that looks good. And then at -1, where is -1 here? -1 is actually going to be 0. You can take my word for that, right? So let me go ahead and just kind of sketch out connecting the dots here for our PDF. It's going to look something like this. So we have a little bit of an increase like so, and then it's going to curve up like this and meet that right there. And so that's roughly what our PDF looks like. Okay, this is the, not PDF, sorry, CDF, the cumulative distribution function. Right? Notice the cumulative distribution function, you're not computing the areas under the curve. If you're looking at f of 1, you're just taking the actual values of those probabilities. So f of 1 would be the height right there, and f of 0 would be the height right there. And you're actually just subtracting those numbers from each other because you already have the antiderivative. All right, let's move on before I keep talking to myself in circles and make this more confusing. Let's do one more example. Let capital X be a continuous random variable with the CDF. Okay, so we're given the CDF here. Capital F of X equals 1 minus 2 over x quantity squared for x greater than 2 and 0 otherwise. 0 otherwise. So the goal, task here, find the PDF. Find the PDF of x. All right, find the PDF of x. So we're given the CDF. So how does one find the PDF here in the continuous case? Remember, in the discrete case, what do you do in the discrete case? In the discrete case, you're going to look for the size of the jumps that you have, if you have any jumps there. In the continuous case, we're going to use this third bullet point that little f of x is equal to the derivative of capital F of x. The derivative of capital F of x. So let's go ahead and take a look at that. So we want little f of x. Little f of x is supposed to be the derivative of capital F of x, or capital F prime. So what do we want to do? We want to differentiate here. We want to take the derivative here. And again, when it comes to taking the derivative, you're sort of really interested in what's happening at this part of the domain, right? Because if I take the derivative of 0, everywhere else, what's the derivative of 0? Well, that's just 0. So I know that the PDF, little f of x, is going to be 0 for everything other than x greater than 2, right? We already sort of know, I can even just, let's start writing on our answer right here. This is going to be equal to something for x greater than 2, and it's equal to 0 otherwise. Again, why is it 0 otherwise? Because what's the derivative of 0? 0. So what's the derivative when x is greater than 2? Well, that would be the derivative of 1 minus 2 over x quantity squared. And now we've got to use our calculus skills to take this derivative. All right. And before I take the derivative here, I might do a little bit of work on the 2 over x squared. Distribute the squared across, so 2 squared is 4. And then dividing by x squared is the same thing as multiplying by x to the negative 2. Using our calculus skills, right, because we always like to work with powers in derivatives and integrals, because the power rules are pretty nice. So now we just take our derivative, and let's see what we get here. The derivative of 1, derivative of a constant is 0. And then what's the derivative of negative 4x to the minus 2? So minus 4 times, what's the derivative of x to the negative 2? You would bring down your exponent and then decrease. Bring down your exponent and then decrease. So what do we have here? Negative times negative gives us a positive 8, x to the negative 3. 8x to the negative 3, or 8 over x cubed. 8 over x cubed. And that is good for x greater than 2. Bingo. There we go. Looks good. 8 over x cubed. All right. Okay. And you can always do a little bit of check on your work here, right? It's very easy to make some mistakes, especially when you're swapping back and forth between CDFs and PDFs. And you start doing integrals and derivatives around the same types of problem, then you might mess up a power rule, and you might make the mistake with the derivative. Maybe we accidentally, use the power rule for integration here, right? Or something like that. So you can always check your work. Feel free to, look up derivatives or something if you need to. We should be able to do all these by hand, but I would always encourage us to go ahead and maybe give us a quick check, right? Quick check here. How do we know that this works? Well, if this is a valid PDF and we didn't screw anything up, then when I integrate 8x to the minus 3 dx, and I integrate this from 2 onto infinity, what should that equal? What should that equal? If this is a valid PDF, that should equal 1, right? So let's go ahead and make sure we didn't screw anything up. So now we're integrating. So we integrate. So the power rule for integration is increase and then divide. Evaluated from 2 to infinity. Evaluate from 2 to infinity. So what is 8 over negative 2? 8 over negative 2 is 4 over x squared. 4 over x squared. And then you'll have a negative sign here. I can absorb the negative in the antiderivative by swapping the bounds of integration. Swapping the bounds of integration. And so then this is going to be, what do we have here? Plugging in 2. This is 4 over 2 squared. Then we have minus 4 over infinity squared. And what do we know about 4 over infinity is that this is going to go off to 0. 4 over 2 squared, that's 4 over 4. Better known as 1. Which indeed does check out. Indeed, that does check out. Okay, that looks good. All right. So just a little bit of a logic check there, just to make sure that looks like we got the correct answer. Okay. All right. I'm gonna leave it at that for now. And see if we can't sort of try to tackle some practice problems from there. If you have any comments, questions about anything that was done in this video, post that in the discussion thread below. And then, of course, as you're working through these mastery points and you have questions about those specific problems online, also post those in the discussion thread below here, because I'm sure we might have quite a few of those. So share the questions and answers with everyone in the class, and let's all help each other out. All right? Good. Looking forward to that discussion, and we'll see you in the next video.